I was so close to done without making anything seriously wrong. Man, I'm so proud of myself. All right, so let's deal with something a little more complicated. Let's say we want to build a cylindrical can out of one single material, probably like aluminum or something, I don't know. And we need to build this can so that it holds 1,000 cubic centimeters, which, by the way, also a liter, but I'm going to keep it as cubic centimeters. And I want to find what dimensions I need to build this can so that I absolutely minimize the amount of material I need to use to actually create a can that can hold 1,000 cubic centimeters. So this is something I'm definitely going to want to draw some pictures for, and you're going to see some incredibly sloppy edits as I erase and redraw it like 400 times. All right, let's go. Yeah, that looks cylindrical. So let's see, we've got this can. All right, now for a cylinder like this, the big important measurements you want to take are the radius, which I'll label R, creative, and the height of the cylinder. Well, actually, I'll label the height right here. I want the radius and the height of this cylinder. Now, what are we trying to find an extreme value for? We're trying to minimize the amount of material used. So let's think about this. I need to create an equation for the amount of material used. Well, this is a hollow can, meaning the material is used to create the exterior of this cylinder, top, bottom, outside part. So that means what I'm actually looking for is I want to minimize the surface area of the cylinder. And of course, we've all memorized the surface area of a cylinder, right? So, all right, let's reconstruct that equation because Lord knows I have to do that every single time. Let's see, what is a cylinder made of? You got a circle on top, a circle on bottom. So you're going to have two circles with radius R. Yes, these look like exactly the same circle. So I've got the area of those two circles contributing to my surface area. Well, that's pi r squared here and another pi r squared here. So I'm going to have these two bits as part of my surface area. But what about the rest? The outside, not the top and the bottom, but just this outside circular bit here. Well, and this is where it taxes my drawing skills to do this. Let's imagine taking this cylinder and unfolding it, just kind of getting rid of the top and bottom and just kind of stretching it out. And you'll see in your sort of mind's picture eye or whatever, as you fold and roll out this cylinder, it rolls out to just be a rectangular sheet. You can kind of just picture it in your head, just roll it out. Okay, so I just need to find the area of this rectangular sheet, and then I've got all of this added together is my surface area. Well, I need a length and a width, rectangle. Well, this side right here, if I'm picturing this just taking down and rolling it out, this is my height of the original cylinder. What about this top part? Well, think about it. I just rolled it out, meaning where this line was in the original drawing is just this top exterior of the circle. This line here is this circle laid flat, which means this is the circumference of this circle. And if we remember our equation for the circumference of a circle, that's 2 pi r. So let's put this all together. Surface area of a cylinder, this circle plus this rectangle. Put that all together and you get this. I got the 2 pi r squareds and I got the 2 pi r times the h. There's my surface area of my cylinder, which I've decided to call a can. Cool. All right, now let me erase some of this stuff. Back in a second. You can definitely see I've got two variables in this equation, so taking a derivative right off the bat, kind of not something I want to do. I want to reduce this down to one variable. But what other equations can I get? Well, I have a constraint. Specifically, I have a constraint in the form of this volume requirement. I need this can to hold 1,000 centimeters cubed. I mean, if that constraint wasn't there, I could just minimize the surface area of this can by just making everything 0. It seems kind of a cheap answer, but it'd work. But I need to make sure that the volume of this can is 1,000 cubic centimeters. So, what's the volume of a cylinder? This one you might actually genuinely have memorized, but maybe you haven't. So how do you think about what the volume of a cylinder is? Well, it's the area of this circle spread out over this entire height, which means it's the area of this circle, which is pi r squared, times the whole height, h. So this is my constraint, pi r squared times h. That needs to be equal to 1,000. Now, the reason I'm using 1,000 for the 1,000 cubic centimeters instead of using 1 for a liter is I'm planning to solve this out so that I get like individual height or radius measurements. And those are going to be in centimeters, so I need to have this 1,000 in units that'll actually make sense in those type of equations. Okay, well, I got my two formulas. Let's get to work. My next step, I want to take this optimization equation, the surface area, I want to make sure it only has one variable. So just to make the algebra easier on me, I am going to, there we go. I'm going to take this constraint equation and I'm going to solve for h because that's just one easy step. I divide both sides by the pi r squared and I get this. This is me solving for h in the constraint equation. Now, it actually doesn't matter which of the two variables you solve for and then substitute back in the equation. But notice if I had tried to solve for the r, I would have had to take a square root at some point, and boy, howdy, is that going to make taking derivatives kind of gross. So let's just solve for h, no square roots necessary. All right. It'll still be gross, I promise, but a different, less disgusting type of gross. So I've got my h, and when I substitute that back in, making a correction here for an error in the PowerPoint that someone pointed out to me already. All right, no, I can find it. There's an R right there. Cool. All right, so I substitute that in for my H and then simplify. What happens is that R that I just drew in cancels with one of the R's in the denominator. The pi's cancel, and I get a 2 times 1,000 to get a 2,000. All right, now I've got my updated area equation, and again, I've left my constraint solved for h because we kind of know now I'm going to eventually have to work backwards to get the h at the end. Now let's find my critical points. So I want to take the derivative of this area formula with respect to r. So let's do that. Now doing it for the first term, not too bad, just one power rule. Doing it for the second term isn't bad either once you recognize that this is 2,000 times r to the negative 1. So hey, it's just another power rule. Going through all that, I get 4 pi r minus 2,000 over r squared. Now I need to find when this is equal to 0. That seems a little grosser. Now, there's a lot of ways to go about doing this, but I'm going to go about the safest way. I'm going to turn this into one fraction. So I'm going to take the 4 pi r term, I'm going to multiply top and bottom by r squared, so I have a common denominator, and I'm going to combine the two terms. And I get this. Now look at this. When is this equal to 0? More importantly, is the denominator ever going to help this thing equal 0? No, it's not. Doesn't matter what the denominator is, its influence alone will not suddenly make this whole fraction 0. This will be 0 when the denominator says it's going to be 0. So when the numerator says, this top part, the good one, says it's going to be 0. So let's find out when our numerator is 0. So let's set that equal to 0. Now, this seems a lot more charitable to solve. Just a little bit of algebra, pull the 2,000 over, divide by the 4 pi, take a cube root, and we get this. This lovely, lovely number, which I will not dare to render in decimal here. We get the cube root of 500 over pi. That number, that is our critical point. Now remember, just because we found a critical point doesn't mean we're done. We need to make sure that we have a minimum here. All right, we need to confirm that this actually is a minimum. So we need to use the first derivative test on this critical point. So let's put this disgusting number up here, and let's apply the first derivative test. So this might seem like a huge ask, but remember, let's do it. There we go. This right here involves me having rewritten my first derivative. So this part of the equation is my first derivative. The r squared on the bottom, that's always going to be positive. So really what I'm doing is I'm looking for when the top part is positive or negative. Now if I plug in a number, so this number right here is exactly when 4 pi r cubed was equal to 2000. If I plug in something less than this, well, 4 pi r cubed is going to be smaller, right? Because r cubed is increasing everywhere, except for 0. So that means my derivative here will be negative. Because 4 pi r cubed will be smaller than 2000, I'll get a negative number. Similarly, if I plug in something larger than this number, 4 pi r cubed will be a bigger number than 2000, and so I will get a positive answer. Now, all of this we can test with, test points. Pick a number smaller than cube root of 500 over pi. Don't know what this is in a decimal expansion, but I'm pretty sure it's bigger than 1. So you can just pick 1 as the test point. And then over here I can pick like, I don't know, 40,000 as a test point. And then just kind of look, yeah, I think that's going to be positive. All right. So definitely confirming here that we have a minimum. All right. Now what do we do? Well, remember, we want to find the dimensions of this can, which means the r isn't the only thing we need. We also need the h. So we're going to go back to this constraint here. This h equals 1000 over pi r squared. And we are going to plug in this number for r. And we get this. Now, if this was a fill-in-the-blank question I was having you do, I'd expect you to not need to simplify this, because, oh boy, that doesn't look fun to deal with. However, since this is a huge thing to write and space is kind of at a premium here, I actually am going to simplify this. This, surprisingly enough, simplifies down to just 2 times the cube root of 500 over pi. Weird, huh? Yeah, you should try and do that. Wonderful exercise. So I have both my dimensions here, my r, my h, which means I can conclude that the surface area is minimized when I have a radius of cube root of 500 over pi centimeters and a height of 2 times the cube root of 500 over pi centimeters. And there we go. I've fully and completely answered the question. There. Now you can do literally every optimization problem.